So, welcome everyone to today's session. I'm Hafidh, and today I'm going to talk to you about heap exploitation, specifically glibc heap exploitation. We will cover the mechanics of the glibc heap allocator and see a specific type of heap vulnerabilities, use after free. And in this talk, I'm going to need your full attention because it may sound complicated at first, but hopefully I will do a good job at explaining this thing. So let's get started by motivating this talk. Now, why are we here? Why are we learning about heap exploitation if we are interested about software security and would like to find vulnerabilities in order to exploit them and fix them? Well, modern systems became hardened and more difficult to attack using classic exploit techniques that became popular since the 90s, like stack-based buffer overflows, for instance, where you just had to write shellcode to the stack and override the return address with the shellcode's address in order to execute arbitrary code and take over the system. Well, nowadays this is no longer possible, fortunately or unfortunately, it depends on the perspective, because a lot of security mitigations were introduced in modern systems. For example, ASLR, or address space layout randomization, was introduced to make memory addresses unpredictable to the attacker. Each time a program is executed, the shared libraries it depends on, its stack, and so forth are mapped in a random memory location. This means that ASLR made classic exploits unreliable without a prior memory leak. To defeat ASLR, one may leak memory address in order to get an idea of the process memory layout and further attack the program. I said unreliable here and not impossible because brute forcing is an option in 32-bit systems where ASLR has low entropy and it only affects 12 bits, which means there's only 4096 possibilities. But in 64-bit systems, brute force is out of the game, even if you do a distributed attack against the process. Another protection which made classic buffer overflow exploits impossible is the introduction of data execution prevention, or DEP for short, also called the NX bit or no execute bit that modern CPUs have. With this protection in place, a process cannot have a memory page that is both writable and executable at the same time. And back in the days, the stack was both writable and executable, and this is what made injecting and executing shellcode in memory possible. But this technique is of course no longer viable, and this is why hackers came up with more creative techniques such as return-oriented programming and so on, where the idea is to reuse code snippets that are already present in the binary and the shared libraries that it depends on. These code snippets are called the ROP gadgets. And there's another protection that made achieving buffer overflow exploits even worse: stack canaries or stack cookies. They kind of act like a trap. Imagine yourself sneaking into a castle, for example, and before reaching the entrance you step on a trap which triggers an alarm system that alerts the guards. So you're essentially caught and your plan is ruined. In our analogy here, stack canaries are traps laid down by the guards, and the door is the critical information present in the stack, like the saved frame pointer, the saved return address of the caller function, etc. In order to defeat the stack canary, a memory leak is needed in order to override the stack cookie with its original value and thus bypassing it. And there's another mechanism that made even return-oriented programming harder to achieve. This is PI, or Position Independent Executable. This setting randomizes where the binary sections are loaded in memory. For example, without PI, when you load a binary in memory, it is always loaded at a fixed location, which is known to the attacker. And this protection makes ROP unreliable without a prior memory leak, because ROP gadgets are inside the binary, and if you don't know where the binary is loaded in memory, you need to get a memory leak before being able to guess where the ROP gadgets are located in memory. And lastly, we have read-only relocation read-only or relro. When this setting is set to full, the global offset table will not be writable, making it impossible to hijack the execution flow by simply overwriting a function pointer in the GOT table. This introduces some performance overhead because the program needs to resolve all the functions it needs at the beginning of the execution to then make the GOT table read-only. This setting is set by default to partial, which means every time you need to execute a function, it is resolved, and then the address of that function in libc, for example, it is placed in the GOT table, and the next time the program uses that function again, it already knows where it is located in memory. This is also called lazy binding. And now that we've seen why modern binary exploitation became harder, let's discuss why we are here. Well, heap exploitation techniques can be used to get memory leaks, which defeats most of the protections we talked about. And usually, heap techniques don't care about most of these protections. For example, stack canaries are out of the game since they operate on the stack. And nowadays, most exploits pulled against day-to-day software that you and I use every day use at least one heap-based bug in their exploit chain in order to achieve arbitrary code execution. For example, in browsers, kernels, PDF readers, video players, you name it. Alright, here's what we're gonna do. We'll see the process memory layout briefly, we'll discuss the heap chunks, bins, and finally we'll talk about the use after free vulnerability and how to exploit it and how to fix it if you're a developer. So, when you execute a program, here's what its process virtual memory layout will look like. On the left-hand side, we have the layout for 32-bit systems, and on the right-hand side, the layout in 64-bit systems. The only notable difference here is the size of the virtual memory. On 32-bit systems, the user space gets 3 gigabytes, while the kernel gets 1. And on 64-bit systems, both the user and the kernel get 128 terabytes. And they are separated by an undefined region. And just remember that the stack grows towards lower addresses, while the heap grows towards higher addresses. This is important to note in binary exploitation. So, what is the heap? Before answering this question, let's talk about how a process may allocate memory first. Say, for example, you have a program that needs 128 bytes of memory. Now, in reality, in Unix systems, Unix-like systems, and probably in Windows too, the only way that this process could ask for such an allocation is by requesting it from the operating system, and specifically the kernel. It does so using the mmap system call, which allocates memory in a unit called a page. And there's also two other syscalls that we will discuss later. They are called brk and sbrk. A page is generally 4096 bytes, or 4 kilobytes. But what if the program needs only 128 bytes? This is wasted memory if the program gets 4096 bytes. And that's exactly where the heap and heap allocators come into play. The heap is a dynamic memory region that grows and shrinks on demand. And it is managed by a dynamic allocator, like ptmalloc, gmalloc, tcmalloc, etc. The first dynamic allocator was released to the public in 1987 by Dougley, and this allocator is named dlmalloc after his name. This allocator had a lot of security issues, but was a very good starting point. In fact, there's a FRAC article that was published, it's called Once Upon a Free, which talks about a vulnerability present in this heap allocator. So glibc, the standard C library, it uses ptmalloc too. And this is the one we will be talking about here. One thing that dynamic allocators should provide is that they should be extremely fast, like lightning fast, because a lot of critical applications depend on these algorithms. Say you have, for example, a game. We all play games. In order to allocate some space for an object in the game, whether it be a player, a chair, a bird, the heap is solicited every time. And if this operation is slow, the performance of the game is directly affected and your gameplay experience is affected also. Alright, how does the program use the heap? As implemented by most dynamic allocators, the heap mainly provides two operations. We can use malloc to allocate some memory of at least size bytes, and when we're done with that memory region, we tell the allocator that we no longer need it by calling the free function with a pointer to that memory region. Once Alright, sorry, I'm back. Yeah, where were we? Yeah, I was saying that in order to release memory to the heap allocator, we say, hey, heap allocator, we no longer need this memory region. You can use it for something else. And we do this by calling the free function and passing in the pointer to that memory region that we were occupying. And there's also other auxiliary functions like calloc, which behaves the same as malloc, except that it zeroes out the allocated memory region. It is kind of equivalent to doing malloc and then using memset to write a bunch of zeros to that memory. Except that calloc doesn't use the TCache, as it considers those free chunks dirty. And we will talk more about TCache in a moment. We also have realloc, which changes the size of an allocation. We pass in a pointer to a previously allocated memory region and the new size. It could be smaller or bigger, it depends. If the pointer passed to realloc is null, it behaves exactly like malloc. Otherwise, it behaves like free if the size is 0. In the rest of the cases, it behaves like realloc. Well, it either grows the heap allocation or shrinks it. Now, how does the heap work? The heap is managed through the BRK and SBRK system calls in addition to the mmap system call. System calls are interface between the user and the kernel. If you don't know about them, that's not a big deal. When the program starts, it doesn't have a heap yet. It's until the first call to malloc or auxiliary functions that the heap comes into existence. First, the BRK system call is used to determine the end of the data segment, like shown here. Then the BRK system call is used to grow the data segment from here, usually by hex 21,000 bytes, which gives birth to the heap. And strace is a Unix utility that traces system calls made by a program. If we use strace and run a program that uses the heap, we will see that when we call malloc or similar functions for the first time, the heap will be created using SBRK and BRK. As you can see here, BRK returns an address. When we pass null to SBRK, it returns the address. This address is the end of the data segment. And then this address plus hex 21,000 is this address, which we pass to BRK. And then BRK asks the kernel to grow the data segment of the process until that address in order to create the heap. Now, when we call malloc, a few things could happen. If there's enough space in the heap and the requested allocation isn't too large, the dynamic allocator will slice off a chunk from the heap and give its address back to the user. If there's not enough space in the heap and the requested allocation isn't too large, the BRK system call is used in order to grow the size of the heap before slicing off a chunk to the user. And issuing a system call requires the involvement of the kernel, which is slow. Finally, if the requested allocation is too large, the dynamic allocator, in order to prevent fragmentation, will request some memory pages from the kernel specifically for that allocation using the mmap system call. Now, maybe you've heard me mention the word chunk before, but I didn't explain what it means. A heap chunk is a data structure defined like this. This is the structure definition from glibc malloc source code. So the first two members represent the size of the previous chunk and the size of the chunk in question. These two are just metadata used by the heap allocator in order to do its job. Next, we have the forward and backward pointers, which are used to form linked lists that we will talk about in a moment. And lastly, we have two other forward and backward pointers that are only used for small and large chunks. Chunks of large size, let's say. We will not care about these two for now. An allocated chunk looks like this in memory. A chunk size can only be a multiple of 16 or hex 10 in hexadecimal. This means that the 4 lowest significant bits are always 0. And this is why glibc uses those bits to encode some more information called the flags or the AMP flags. The A flag tells the allocator whether this chunk belongs to the main arena or not. The concept of arenas is something on its own. We will not talk about it in this session, so let's just ignore it. The second flag, the M flag, tells us if this chunk was obtained as a result of a call to mmap or not. As we said before, if the allocation is if we request an allocation that is too large, the glibc heap allocator will use mmap in order to request memory pages specifically for this allocation. And if it is the case, this M flag is set to 1. Otherwise, it is set to 0. And the least significant bit tells the allocator whether the previous chunk is empty or not, or free or not. If it is occupied, this bit is set to 1. And for your information, when we call malloc with the size of an allocation, it will return a pointer right here in mem. It will return a pointer to the user data, not the heap metadata. Once a chunk is freed, once we call free with the address of a chunk, it will look like this. Now, if the chunk was allocated through mmap, it is given back to the operating system through the mmap syscall. Otherwise, it remains on the heap as a reusable chunk. And the allocator places forward and backward pointers, these pointers, on that chunk that will form the linked lists of free chunk, also known as bins. So what are bins? They are singly or doubly linked lists that store previously freed chunks, and they exist solely to improve the performance of the heap allocator. This is a performance improvement to the heap allocator. Instead of slicing off a chunk from the heap, which takes a few operations, kind of slow, the allocator will return a chunk directly from a linked list, which is really fast. Here's a reminder for people who didn't do computer science about singly and doubly linked lists. In linked lists, each node has a pointer along with its data that points to the next node in the list. The first node that no other node points to is called the head of the list, and the last node that doesn't point to any other node is called the tail of the list, and its next pointer is set to null. For doubly linked lists, it's the same concept except that these lists are bidirectional. We have an additional member in the structure, which is a pointer to the previous node in the list. So the head of the list has its previous pointer set to null, and the tail of the list has its next pointer set to null. Now we will discuss the types of bins. There are 5 types of bins. There's the TCache bins, or per thread cache, which were introduced in glibc 226, but they gave up a lot of security checks in favor of performance. There's also fast bins, unsorted bin, small bins, and large bins. We will start with TCache bins. The concept of TCache was introduced to speed up small allocations made by individual threads. Before TCache, threads used to use the same bins for small allocations. They used to use the same fast bins, for example, which means there was concurrency problems, meaning mutexes had to be used. And for people who didn't do a computer science class, mutex is a mutual exclusion. It's a way to lock down a resource in order to not have a concurrency problem where 2 threads access the same resource at the same time, and things could go wrong. And this usage of mutexes, this blocking between threads, was slowing down the execution considerably for multi-threaded programs. TCache bins are singly linked lists that operate in a LIFO manner. LIFO means last in, first out, which is exactly like the stack works, for example. Meaning that addition and deletion happens from the head of the list. Every thread has its own set of TCache bins, and each bin holds a maximum of 7 chunks of the same size. And there are 64 TCache bins per thread. In 64-bit systems, each of those bins have chunks of sizes from hex 20 bytes, the smallest chunk size possible, to hex 410 bytes, with an increment of hex 10 between the size of of the chunks. And these sizes include the hex 10 bytes of metadata that we saw earlier, which are used for the size of the chunk and the size of the previous chunk. And lastly, TCache bins act as a caching layer to fast bins and small bins. They cover their entire size range. The TCache is mainly managed using two structures. The first one is the TCache per thread struct, which contains an unsigned short integer array of size TCache max bins. TCache max bins is set to 64 in glibc source code. This array is called counts. It stores the number of free chunks in each TCache bin. For example, the counts array at index 0, it stores the number of chunks in the TCache bin of size hex 20. And the entries array is the second member of this structure. It is an array of pointers. These pointers are the heads of the TCache bins. For example, the entries array at index 0 stores the pointer to the head of the first chunk in the TCache bin of chunks of size hex 20. So basically, it points to the free chunk of size hex 20 located in the TCache bin. The entries array is kind of redundant, as you can see, because we can count how many entries, how many free chunks are inside a bin simply by traversing the linked list until we get to null. But this was added for performance reasons. There is a space-time trade-off here because we use more space. The counts array is 64. There's 64 elements, and each element is a uint16, which means 2 bytes. So there's 128 bytes of memory occupied. So we occupy a more space here, in this case 128 bytes, in order to improve performance. And each entry in the TCache bin or each node in the singly linked list is defined like follows. There's a next pointer that points to the next free chunk in the list, and there's the key. This key pointer points back to the TCache structure that we saw at the beginning. And this key pointer was added as a security measure in order to prevent double free vulnerabilities. And we will not cover double free vulnerabilities in this talk. Let's stick to use after free. And also, each TCache entry starts at the user payload, meaning after the metadata. Next, we have fast bins. Fast bins are really similar to TCache bins, except that they are shared among all the threads. There are 10 fast bins in glibc, but only 7 of them are used for some reason. I don't know why. And each bin is a singly linked list that works in a LIFO manner, meaning addition and deletion happen from the head of the list. Each bin holds chunks of the same size, and the first bin holds chunks of size hex 20 bytes, while the 7th bin, the last bin, holds chunks of size hex 80 bytes, an increment of hex 10 again. And of course, these sizes include the heap metadata. Fast bins are managed through the malloc state structure and specifically using the fast bins Y array that holds pointers to the heads of the linked lists. For example, fast bins Y at index 0, it holds the pointer to the head of the fast bin which holds chunks of size hex 20 bytes. I hope this makes sense. We will see a great animation in a moment which explains these in details. And a fast entry, just like TCache entries, starts at the user data, not the chunk metadata. And fast bins are used when the corresponding TCache is full. So now let's see the behavior of TCache bins and fast bins. Here we have a simple C program that starts by allocating 9 chunks of size hex 10 bytes each, meaning that the chunks will be of size hex 20 bytes because of the heap metadata that we discussed. And next it will free 7 of these allocations. And lastly, it will free the 2 remaining allocations. At the beginning of this program, the heap doesn't exist yet because we didn't call any function like malloc or calloc, realloc. So it doesn't exist yet. But when we call malloc for the first time, the heap is born. At the start of the heap, there's a chunk. There's a chunk that you can see here that was allocated for the TCache per thread structure that we saw earlier. We can see the counts array is initially all zeros because all TCache bins are empty. And in the entries array, which contains the heads of the TCache bins, every pointer is set to null because initially all the TCache bins are empty. The red rectangle is the allocation that we just made, the allocation made by the user. We can see that the size field is hex 21, which is hex 20 for the size. And the least significant bit is for the flags, which we'll discuss in a moment. This hex 20 is the size of the metadata, which is here, plus the hex 10 passed to malloc. And malloc returns this pointer, which ends with 2A0, not 290. The pointer, this PTR0, points here. And why is it hex 21 instead of hex 20? We said that there's the AMP flags. And if you remember, the least significant bit is the P flag, which means prev in use. This bit is set in this case because the previous chunk, which holds the TCache per thread structure, is occupied, so it is in use. And this is why this is hex 21 instead of hex 20. This chunk right here was sliced off from the top chunk, this chunk, also called the wilderness. Each time we do an allocation, the size of the top chunk decreases. So, let's make our second allocation. The top chunk size decreased again, and a new chunk of size hex 20 appeared, just like before. And the top chunk moved down, or up, because these are greater addresses. Then we do the third allocation, and the fourth allocation, the fifth, the sixth, same thing. The seventh allocation, the eighth, and finally we do the ninth allocation. And now what happens when we start freeing chunks? What happens when we start calling the free function with the pointers to these chunks? When we free the first chunk, here's what happens. First, in the TCache per thread struct, the counts array that you can see here at index 0 is now 1. This is because the chunk that we just freed became part of the TCache bin of size hex 20. We can see in the entries array that the first pointer here, which is the head of the TCache bin of size hex 20, is now pointing to the chunk we just freed, meaning that this chunk is now the head of the linked list and is currently the only free chunk. And you may be wondering why this pointer is all 5, instead of 0, because we said this is a linked list and the next pointer points to the next free chunk in the list. And since this TCache bin currently only have one chunk, the next pointer should be null. Why is it all 5 and ends with 9? This is some feature that glibc developers added recently. They added a protection to make use of ASLR in order to protect pointers. This is actually the address of this memory region, of this quad word. The address shifted by 12 and XORed with the actual pointer. You can verify that by yourself. If we take this address, we shift it by 12, which means we get rid of 2A0, and we XOR it with all zeros, it remains 555 until 9. And this is exactly what the pointer is. Before being used, it will be deobfuscated, let's say, by glibc, then used in order to do its job. And the second element, it's the key. We said that this key points back to the TCache per thread struct, and indeed it does. This pointer ends with 9010, and the address of the TCache per thread struct is 9010 here. When we free the second chunk, the counter is incremented to 2, and the head of the TCache bin is updated because we said it works in a LIFO manner, which means addition and deletion happen from the head of the list. Now, the head becomes our newly free chunk, and its next pointer points to the previous chunk, forming a singly linked list of 2 elements. The same thing happens for the third chunk and the fourth, the fifth, the sixth, and finally the seventh chunk. Now, the TCache bin of size hex20 is full because it contains 7 chunks. We can see that the counts array at index 0 is 7 for now. Now what happens if we free the 8th chunk? Since the corresponding TCache is full, the fast bin of the same size takes the lead now. The head of the fast bin of size hex20 becomes our newly freed chunk. And the fast bin's Y array in the malloc state structure at index 0 contains the pointer to the head of the linked list. And now it points to this chunk that we just freed. And for the second chunk, the head is updated and so on, just like the TCache. Now the unsorted bin. There's only one unsorted bin and it's a circular linked list, meaning the tail of the list points back to the head. When small and large chunks are freed, they initially end up in this list. And for instance, small and large chunks, small chunks begin from hex 90, I guess, and large chunks I forgot from where they begin. But when freed, they initially end up in this list. Given, of course, if we are talking about small bins, given that the corresponding TCache is already full, because we said that TCache covers both fast bins and small bins. If we have a small chunk, which we free, and the corresponding TCache is not full, this chunk will land in the TCache, not the unsorted bin. Small chunks only fall in the unsorted bin if the corresponding TCache is already full. And the primary purpose of this bin is to act as a caching layer to speed up allocation and deallocation requests. And chunks placed in this bin may be considered for coalescing with adjacent free chunks, then placed in the corresponding small or large bin, or become part of the wilderness when merged with the top chunk. The interesting thing for us, however, is that the forward and backward pointers of a chunk that resides in the unsorted bin point back to the bins array located in the main arena, which is an instance of the malloc state structure that we saw earlier. And this is useful for us to leak a libc address and defeat ASLR, because main arena is a global variable in libc, which means if we get its address, we get a libc address. And if we know the offset, we can calculate the libc base address and use that to defeat ASLR. Now we know where all ROP gadgets are located, and we can use them to build a ROP chain or whatever. The remaining two types of bins are small and large bins. They are doubly linked lists that we don't usually use a lot in heap exploitation, although there are techniques that rely on them. If you would like to know more about them, visit the article written by Daval Kapil. It's like a book, a small book about heap exploitation. It's a good starting point if you read it. Alright, now that we have an idea about the heap shenanigans, let's dive into use after free. Use after free, known under the identifier CWE416. CWE is for Common Weakness Enumeration. It's a database of weaknesses in softwares, and use after free is one of those weaknesses, and its identifier is CWE416. This is a vulnerability that occurs when the program tries to access previously freed memory, either with a read operation or a write operation. Let's see through an example. Here we have yet another simple C program that takes a name as a command line argument. In our case, we execute this program and pass in some A's, 8 A's. It allocates a chunk for it using calloc, which means it's exactly the same as malloc, and then memset with 0. And copies the name into that chunk using strncopy. It then frees that chunk and uses it afterwards during a call to printf. This is just an illustrative example, but it will help you understand use after free. Now, what could go wrong? First, the call to calloc. We have now allocated a chunk of size hex20, including metadata. That the name pointer now points to that chunk that we just allocated. like we can see with this arrow. After that, we copy the name into that chunk. We can see a bunch of hex 41 in the heap chunk. That's the A's. Next, we free our chunk. We can see the forward and backward pointers in our chunk. These two pointers that we saw earlier. Now the interesting thing is that the name pointer still points to that chunk even if it is free. So when we issue the call to printf, we will actually print the forward pointer, and we have an information leak. And this leak is actually an obfuscated heap pointer, which we can use to calculate the heap base address. And using the heap base address, we have an exact idea of how the heap layout is, because glibc heap is deterministic. If we run a program multiple times, we will get the same heap layout every time. This happened because we had what is called a dangling pointer. Name was still pointing to a memory region even after it got freed. And then during its execution, the program dereferenced that dangling pointer, which is really bad. It could lead to memory leaks or arbitrary writes, which leads to arbitrary code execution. Now, how to protect against this? The remediation. We can fix this vulnerability by simply setting the pointer to null after calling free. Of course, this program is very simple. We can do a check before calling printf, but in complex programs where the code base is huge, these mistakes happen a lot. And you don't just fix this problem by doing static code analysis. This is not like stack-based buffer overflows. These bugs rely on the logic of the program. It needs, in order to trigger a use after free vulnerability, you need to go a specific execution path. This is generally found using symbolic execution by exploring various execution paths possible by the program, but this takes time, of course. As I said, we can fix this vulnerability by setting the pointer to null after we free the chunk it points to. That way we no more have a dangling pointer. And this way, even if the program dereferences this null pointer later during execution, the worst that could happen is a crash due to a null pointer dereference. And the null address is of course not mapped. And this causes a segmentation fault. In our example, if we execute this patched program, we allocate our chunk using calloc first, and then we copy the name into it, and then we free that chunk. After freeing it, we set it to null, so it no longer points to that free chunk. Now, when passing that pointer into printf, we got no information leak. Printf will simply print out null since it found the pointer to be null and couldn't dereference it. So it printed out null. So, what did we learn? Use after free can be used to achieve arbitrary read and arbitrary write, which are very strong exploit primitives that can lead to remote code execution. Use after free is the basis of a good number of 0 days nowadays. Heap exploitation is surely not easy, and there's many dynamic allocators to explore. It thus requires practice to achieve proper mastery. For example, Google Chrome uses tcmalloc. tcmalloc is developed by Google. Firefox, I guess it uses gemalloc. iOS also uses gemalloc. In Linux, glibc is used generally. And heap techniques can vary from heap. Sorry? Yeah, heap exploitation is surely not easy. There's many dynamic heap allocators, like I said. And ptmalloc2, the dynamic allocator that we just discussed today, is just one of many heap implementations. And heap techniques can vary from heap implementation to another, but the basic concepts and the general idea applies to all of them. And lastly, the security/performance trade-off is a never-ending cycle. glibc developers always try to make things faster and faster, which might break security. Then they start adding patches and fixing things to correct those mistakes, And the circles goes on and on. It never ends. And if you're interested to learn more about heap exploitation or binary exploitation in general, here are a few great resources. First, there's Pond College, which inspired me to give this talk in the first place. It contains everything you need to learn binary exploitation, like literally. The instructor is a highly skilled person called Zardius. He's the team captain of Shellfish and the leader of the Order of the Overflow, which were the ex-organizers of DEF CON. And I'm sure you heard about DEF CON. It's a hacking competition, the most tough hacking competition in the world, which is held in Las Vegas. And this guy makes challenges and gives talks. So yeah. There's also the blog posts of the Valkapil that I mentioned earlier. It's a very good resource to learn heap exploitation. I also invite you to skim read through glibc malloc source code in order to understand the internals much better. There's also some great write-ups from PicoCTF written by Faraz. They are very detailed and they should answer most of your questions. There's an article written by Ray Dancia, two popular GitHub repositories. There's How to Heap from Shellfish and MBE or Modern Binary Exploitation from RPI-Sec. There's another blog written by a guy in Tuxedo which contains a structured binary exploitation course. It's a really good resource. And then there's some FRAC articles. There's the article I mentioned about the malloc, Once Upon a Free. And there's the article called Malloc Dim Maleficarum, which introduces most of the heap techniques known today, like House of Force, House of Spirit, and so on. And lastly, there's some FRAC articles that you may want to look at. And if you want to see the list of 0 days disclosed through the ZDI program, check out the last link. Just type in use after free, for example, in the search bar, and you will see some interesting findings, for example, in Acrobat Reader, in VLC, etc. So thanks for your attention. If you have any questions, I'm all ears. I will be answering either through the chat or using the mic. Thanks.